Hello everyone, today we're continuing the topic of operational amplifiers and their applications as linear amplifiers. So we are going to look at the application of operational amplifiers as a difference amplifier and as current sources. So the first application that we're going to look at is a difference amplifier. This op-amp circuit is used to amplify the difference between signal V1 and voltage signal V2. So let's use the node voltage analysis method to calculate an expression that relates V out to V1 and V2. First golden rule of op-amp is that IP is equal to IN, that's equal to 0. The second golden rule of op-amp is that in the presence of negative feedback, which we have in here, V out is connected to the inverting terminal of op-amp. Vp is equal to Vn, that's equal to 0. So from there, at node Vn, I can write Vn minus V1 divided by R1 plus Vn minus V out divided by Rf is equal to 0. Then at node P, Vp minus V2 divided by R1, R2 plus Vp minus 0 divided by Rs equals to 0. Now, because Vp and Vn are equal to each other, I have from here Vn equals to Vp, and that's equal to Rs divided by Rs plus R2 times V2. So if I substitute for Vn in the first equation, I get V out is equal to negative Rf over R1 times V1 plus 1 plus Rf over R1 multiplied by Rs divided by R2 plus Rs multiplied by V2. Okay, now if Rs divided by R2 is equal to Rf divided by R1, in that case V out is going to be simplified to Rf over R1 multiplied by V2 minus V1. So it amplifies this op-amp circuit amplifies the difference between V2 and V1. Okay, so let's look at the second application of this op-amp circuit as a transconductance amplifier or a current source. In this circuit, the output, which is the current that flows through the load, is proportional to Vi, and we're going to show that it's proportional to Vi and it is independent of the value of RL. As a result, it's a transconductance amplifier or a current source. In a current source, the amount of current from at the output of the current source is independent of the value of RL. So first and second golden rule of op-amps, we can use both of them because of the presence of negative feedback. The output is connected to the inverting terminal at the input side. So IN is equal to IP, that's equal to 0. Because it's ideal op-amp, I can write IN is exactly equal to IP. For the case of non-ideal op-amp, a non-ideal op-amp, IN is almost equal to IP, and that's equal to 0. So Vn is going to be equal to Vi from the second golden rule, and this is my Vn node voltage at the inverting terminal, and IN is equal to 0, IP is also equal to 0. Okay, so Vn is equal to Vi, node voltage equations at the inverting terminal. So Vi divided by R1 is equal to IL, this current that flows into this node, so that's going to be equal to IL. As a result, VI over IL is equal to 1 over R1. So this the output current is independent of the value of RL, and it's set by choosing the right value for the resistor R1. Okay, so the load in this current source is a floating load. In other words, it's not connected to the ground, but sometimes we need to we would like to have to use, or we have to use a voltage, a load that's grounded to make sure that the current source can be used for a load that's grounded. We can use this configuration. So this is a grounded current source. As you can see, this RL in here is connected. One end of the RL, one terminal is connected to the reference node, and the other terminal is connected to the output of the circuit. So let's label the current, and this is I1, and this I will label it as I2, and I would label this one I3, and this is I4, and the current that goes through the load is called IL. So this is VP, and this node is VN. And okay, so again, first golden rule is that IN is equal to IP, that's equal to 0. And the second golden rule is that VP is equal to VN. So if I write the KCL at the VN node, at the inverting terminal, I1 is going to be equal to I2. That's what KCL tells me. And at this node, at BP node, I can write I3 is equal to IL plus I4. I'm going to name this one equation 1, and this is equation number 2. So from equation number 1, if I want to write I1 in terms of node voltage equation, that's going to give me negative Vn and divided by R1. That's equal to Vn minus Vout divided by Rf. Now from equation 2, I have Vi minus Vn divided by R2 is equal to IL plus Vn minus Vout divided by R3. Now, so let's define a dummy variable B, and let's say Vn minus Vout is equal to B, and the same goes here. So it's going to help us simplify the calculations, or organize our calculations. So from equation 1, I have negative Vn over R1 is equal to B over Rf. So we're going to continue the calculations by assuming that Rf over R1 is equal to R3 over R2, and this is the condition for this circuit to work and to act as a current source. So we're going to design this, or choose the value of these resistors such that Rf over R1 would be equal to R3 over R2, and if it is so, then the circuit is going to act like a current source. So I'm going to replace Rf over R1 with R2 over R3. So let's do that and see how IL is related to Vi. So negative Vn over R1 is equal to B over R1 is equal to B over Rf. From there, negative Vn is going to be equal to B over Rf divided by R1. So now we said in R1 we're going to set RF over R1 to be equal to R3 over R2. From there, because RF over R1 we set it to be equal to R3 over R2, then negative Vn is going to be equal to B over R3 divided by R2. And from there, I know that B is equal to negative R3 over R2 multiplied by Vn. So I'm going to replace this value in the equation 2 and calculate the IL over Vi. Okay, so from equation 2, I have Vi minus Vn divided by R2 equals to IL plus Vn minus Vout divided by R3. So I'm gonna write it, this one equals to IL plus B divided by R3, and that's equal to IL plus negative Vn divided by R2. From here, Vi divided by R2 is equal to IL, or in other words, IL divided by Vi is going to be equal to 1 over R2. So the gain value, or the value of output current divided by input voltage, is equal to 1 over 2, and it is independent of the value of load resistor. So it acts like a current source.